Hi, organic chemistry again, haloalkanes and haloarenes. We are going to do more revision on PYQs from haloalkanes and haloarenes. Hi, I'm Prasanna. Welcome to my platform, ChemsMart. The questions for today are, question number 1, which compound in each of the following pairs will react faster in SN1 reaction with OH minus? You know, SN1 reaction is all about the formation of carbocation, right? SN1 reaction undergoes a mechanism in which there is a carbocation formed. So, SN1 mechanism depends on the stability of the carbocation, if you remember. So, we have to compare in which case carbocation will be more stable. That compound will undergo faster SN1 mechanism. Compare these two. You know, this is halogen is connected to sp3 carbon, which is in turn connected to sp2 carbon. You know, this carbon is sp2. sp3 carbon connected to sp2 carbon and halogen connected to that sp3 carbon. That is allylic halide. And this is the normal alkyl halide. You know that. So, you know, allylic and benzylic carbocations are stabilized by resonance. So, this will undergo faster SN1 reaction because it is forming allylic carbocation during the reaction, which is more stable than the alkyl carbocation, which is produced from this one. Clear? Second one. This is CS3 tri-CCl, which is a tertiary alkyl halide. Tertiary alkyl halide. And CS3Cl, it is methyl halide. And what is the order of stability of carbocations? Order of stability of carbocations is tertiary carbocation more stable than secondary, which is more stable than primary. So the carbocation formed by tertiary alkyl halide, which is a tertiary carbocation, will be more stable than, which is methyl. Methyl halide is the least. Okay, so methyl carbocation will be the least stable. So this one will form a more stable carbocation compared to methyl carbocation, and this will undergo faster SN1 mechanism. Clear? Now, the next question. Which of the following is an appropriate set of reactants for the preparation of 1-methoxy-4-nitrobenzene, and why? You have this question in the textbook. It is a textbook question. You know, here in this particular case, methyl bromide is reacting with this ONA. This is sodium phenoxide area. Okay, 4-nitro sodium phenoxide. Here, halogen is directly connected to benzene ring. So, this part, it is aryl halide. And there is a partial double bond character here. You know that. And when an aryl halide is reacting with sodium alkoxide, the substitution becomes difficult because of the partial double bond character of the aryl halogen bond. So, being an aryl halide, it cannot undergo substitution easily. But in this first case, the alkyl halide is used, not aryl halide, for the preparation of the ether. So, this Na can easily go with this Br and CS3 can get connected there. So, you will get the required ether. So, the correct pair to produce 1-methoxy-4-nitrobenzene is this one, because it is sodium phenoxide, not aryl halide, which is used. Clear? So, this will be the correct answer. Now, next one. Predict the stereochemistry of the product formed if an optically active alkyl halide undergoes substitution reaction by SN1 mechanism. I have told you SN1 mechanism is all about the formation of a carbocation, right? And carbocation, you know, it is sp2 hybridized. So, this will be the shape of the carbocation, trigonal planar with bond angle 120 degree. Okay. So, when we have a trigonal planar carbocation formed during SN1 mechanism, this carbocation can be attacked by the nucleophile from either direction. There is it can be attacked from left or right, or from top or from bottom. Equal chance. That means the product formed will have two enantiomers, plus and minus, or dextro and levo enantiomers in equal proportion. That means you will be getting a racemic mixture. And you have studied SN1 mechanism is always accompanied by racemization. If it is SN2, there will be inversion of configuration. But in SN1, it will be racemization. So the product formed will be a racemic mixture. Clear? Okay. Now, the next question is, name the instrument for measuring the angle by which the plane polarized light is rotated. And that instrument you have studied, which is measuring the optical rotation, that is called polarimeter. What? Polarimeter. Now, the next question. Predict the major product formed when 2-bromopentane reacts with alcoholic KOH. That is 2-bromopentane. Let's see what is 2-bromopentane. 2-bromopentane. It is treated with alcoholic KOH. We have studied in the previous session that alcoholic KOH is the reagent used to make the alkyl halide undergo dehydrohalogenation. And dehydrohalogenation is a beta elimination, right? So if it is undergoing beta elimination, what will happen? Let's see. You know, halogen connected carbon, this is alpha. Then we have two beta carbons. This is beta, this is also beta. That means we have two chances of formation of alkenes through dehydrohalogenation of this 2-bromopentane. Let's see what these are. Suppose this beta hydrogen is eliminated with this alpha halogen. What will you get? Then the double bond will be between this alpha and beta, right? So we'll be getting CS2, double bond CH, then CS2, then CS2, CS3. So this will be 1, 2, 3, 4, 5. It will be pent 1-ene. This is the product if this is the elimination happening. Now suppose we are doing the other chance of elimination. What is that? This halogen is going with this hydrogen. That means this beta hydrogen is involved in elimination. Now a double bond will be created between this alpha and beta. Alpha, beta unsaturation here. So the product formed will be CS3, CH double bond CH, then CS2, CS3. That means you are getting pent 2-ene, right? So we are getting a mixture of two alkenes from this beta elimination possibilities. What are they? We are getting pent 1-ene and pent 2-ene. How will we know which one is the major product? One is major, one is minor. You have to apply Seitz-of rule. We have discussed in one of the previous sessions. What is Seitz-of rule? When different alkenes are possible through such an elimination, that alkene in which the carbon atoms holding double bond are more alkylated will be the major product, and the other one will be the minor product. Seitz-of rule. So let us compare. Here, these are the two carbons holding the double bond. On this carbon, there are two hydrogens only, no alkyl group. On this carbon, there is one hydrogen and a normal propyl group. So there is an alkyl group on that carbon. What about this one? These are the two carbons holding the double bond. And what are the groups here? The groups here are, on this carbon, there is one hydrogen and a methyl group. There is an alkyl group on that. On this carbon also, there is one hydrogen and an ethyl group. So when you compare these two, which one is more alkylated? This one is more alkylated versus this one where both are hydrogens on one carbon of the double bond. So we say pen-2-ene is the major product in this case compared to pen-1-ene. This will be minor product and this one will be the major product. Clear? Practice. Okay? Now, let's see what the next question is. The next one is give one use of iodoform. Very simple question. It is given in your textbook in the polyhalogen compounds area. In olden days, we used to use this iodoform as an antiseptic because it is liberating iodine. Due to liberation of free iodine from iodoform, it was used as an antiseptic due to antiseptic properties. And that antiseptic property is connected to liberation of iodine, not iodoform as such. And nowadays, we have better alternatives because this iodoform is having an unpleasant smell. Okay. Anyway, what is the use of iodoform? It was used as an antiseptic. Clear? I hope all these questions we discussed in today's session are all clear to you. Just practice. And please make sure to like, share, and also subscribe to my channel. See you inside for the next session. And till then, bye.